Imagine this. A single point of light gliding across the darkness, following a path no planet or comet from our solar system has ever taken, moving with a calm and unsettling confidence, as if it already knows its origin and its destination, before anyone can name it. A quiet question rises beneath the surface. What if there is something out there that does not follow any rule we understand? What if it never belonged to the solar system at all? We have seen interstellar visitors before. From Oumuamua with its unnerving acceleration, to Borisov with its familiar comet heart. Yet neither prepared us for this one. 3. I Atlas does not behave like a wanderer. It behaves like something with intention. Its first clues are already wrong. A composition strangely rich in nickel when comets should carry iron. A rotation so steady it feels engineered. A body that breaks into evenly spaced fragments instead of shattering at random. And a dust structure bending toward the sun instead of away from it. Just when you think the mystery has reached its limit, a quiet realization settles in. The strangest part of 3I Atlas has not been explained. It may not have even been discovered yet. Are you ready to listen? It began as a faint moving spark detected by the Atlas survey in Hawaii. A system designed to scan the sky for dangerous near-Earth objects. Not for visitors from the deep void. Yet, on that quiet night, the system caught something that did not belong to any known family of comets or asteroids. When astronomers confirmed its hyperbolic trajectory, they gave it a new designation. It became the third interstellar object ever recorded, which is why it carries the name 3I Atlas. Third interstellar, and traced back to the very survey that spotted it. From the start, it refused to behave like comets born inside the solar system. It lacked the familiar signs of water-driven activity that domestic comets always show. Its brightness curve was uneven and its structure looked unusually solid. To complicate everything, the earliest observations arrived during a period when the United States federal shutdown limited access to scientific resources and delayed data processing. Weeks passed before proper analysis could begin, which left a strange silence around the object at the exact moment the world most needed clarity. And the question lingers quietly. What exactly did that delay obscure? The more telescopes focused on 3I Atlas, the stranger it appeared. Its brightness rose and faded in a rhythm far too controlled for a natural comet, which normally flickers unpredictably as sunlight heats pockets of ice. But Atlas showed a pattern, as if something beneath its surface was modulating the light. It also lacked a clear gaseous coma, the glowing cloud of water vapor that every water-rich comet produces when approaching the sun. Instead, observers saw a lean structure with an unexpected twist. Its dust stream bent inward, forming an anti-tail, a geometry that requires a rigid core rather than a fragile body of ice and dust. The way it reflected light supported this suspicion. Instead of scattering brightness like a fluffy frozen object, Atlas reflected it with a firmness that felt closer to metal or stone. The more data arrived, the more it resembled an engineered surface rather than a melting comet. And once that idea settles into your mind, it raises a single unsettling thought. It almost looks as if it was designed to reflect light. When astronomers examined the spectral fingerprint of 3I Atlas, one feature stood out immediately. The signature of nickel appeared far stronger than expected. dominating the readings in a way no natural comet ever has. Ordinary comets from our solar system carry iron and large amounts of water ice, but Atlas behaved as if iron were almost absent and nickel had taken its place. This imbalance forced scientists to consider extreme origins. Material this rich in nickel is usually found in environments that experience incredible heat. The kind produced near a collapsing star or inside the shockwave of a powerful supernova. If Atlas truly carries such a composition, then it was forged in a crucible far more violent than anything found in our planetary neighborhood. The idea lingers quietly at the edge of scientific conversation. Either it survived a stellar catastrophe, or something refined it deliberately. The next puzzle emerged when scientists searched for the familiar signs of water sublimation, the process that produces a glowing coma around normal comets. Yet 3I Atlas released almost no water vapor even as it approached the Sun. Instead of water, astronomers detected unusually high levels of carbon dioxide, far beyond what current comet models predict. This chemical imbalance hints at a structure capable of shielding internal ice or preventing volatile materials from escaping. No comet formed within the solar system has ever shown behavior like this, which suggests that Atlas was built or formed under conditions vastly different from anything known. The more the data accumulated, the clearer the implication became. The water inside Atlas was not allowed to escape. The rotation of 3I Atlas became one of the earliest clues that something was deeply unusual. Its spin repeated with a precision that comets simply do not have. A rhythm steady enough to resemble a metronome instead of a melting fragment of ice and dust. Most comets wobble as jets of gas erupt unevenly from their surface, each burst creating tiny pushes that disrupt the rotation. But Atlas showed no signs of these natural imbalances. Its surface remained silent, and nothing seemed to interfere with the motion. The more astronomers measured, the more its rotation hinted at symmetry, as if the object carried a balanced internal structure designed to keep its motion centered. A few scientists quietly drew comparisons to tumbling control, a technique used by spacecraft to stabilize themselves during long journeys through space. The implication was subtle yet difficult to ignore. Was Atlas stabilizing itself, or was something inside it maintaining stability for a purpose we have not yet understood? The next mystery revealed itself through the dust streaming around 3I Atlas. Instead of forming a classic tail that stretches away from the Sun, Atlas displayed a striking anti-tail, a luminous structure bending toward the light rather than fleeing from it. This phenomenon is rare and only appears when large dust particles follow a very specific orbital geometry, one that requires a stable and rigid core to maintain its form. Yet, in the case of Atlas, the anti-tail was not just visible, it persisted for an unnaturally long period, holding its shape as if anchored to a solid frame. This defied expectations because fragile icy comets do not maintain such persistent structures. They crumble. They shed material. They lose coherence. Atlas behaved differently, as though the dust were responding to a body more rigid and unified than a natural comet nucleus. The more astronomers studied it, the more the pattern felt deliberate rather than accidental. A comet is not supposed to have an anti-tail like this, and yet Atlas displayed one boldly, as if announcing that it was built differently from the start. The moment astronomers began comparing amateur photographs of 3I Atlas, one detail rose above everything else. The object was not splitting at random the way natural comets usually do. Instead, observers around the world consistently captured the same sight. 16 distinct fragments drifting away from the core at nearly equal intervals, arranged in a formation that felt more like a sequence than an accident. Natural breakups caused by thermal stress create uneven shards because pressure builds unpredictably across a fragile nucleus. Yet Atlas displayed a geometry that suggested balance, as if the object fractured along predetermined weak points. Some amateur astronomers quietly wondered whether these stress points were inherent to its structure, designed or formed long before it entered our solar system. The idea is unsettling because it hints at a level of internal order rarely seen in natural bodies. It leaves one haunting question suspended in the dark. Why would an interstellar object break apart in a pattern? When 3I Atlas swept past Mars, astronomers recognized that the flyby created a near-perfect opportunity to capture high-resolution images. The object passed at a distance ideal for the powerful optics aboard spacecraft orbiting the planet. It was the kind of alignment that happens rarely in interstellar studies. Yet, when NASA released the first images, they appeared faint, blurred or surprisingly delayed. This puzzled many because instruments like HiRISE and the Mastcam systems on Perseverance are capable of extraordinary clarity. Amateur communities began to speculate that better images existed but had not been shared. The discussion intensified when a few observers claimed that certain released photos showed signs of artificial softening, as if details had been deliberately muted. Whether these suspicions are justified or not, they echo a deeper uncertainty. Perhaps what the instruments saw during the flyby was something the agencies were not ready to explain. The discovery of 3I Atlas arrived at an inconvenient moment. The United States federal shutdown had just begun, which meant that many scientific offices were partially closed and critical data channels were operating at reduced capacity. As telescopes tracked the interstellar visitor, the information they gathered sat in limbo, waiting weeks before full analysis could resume. When NASA finally released an official statement, the description was brief and conservative. It labeled the object as a natural comet and offered no additional context. There was no discussion of the nickel-dominated spectrum, no mention of the strangely stable rotation, and nothing about the persistent anti-tail. For many observers, the silence was louder than any explanation. It hinted at uncertainty, caution, or perhaps a lack of consensus behind the scenes. Whatever the reason, one conclusion felt unavoidable. When science does not speak, silence becomes the answer. The arrival of Oumuamua in 2017 reshaped the scientific landscape. Its elongated shape, uneven reflection, and unexplained acceleration ignited debates that lasted for years and opened the door to discussions many institutions had avoided. When 3I Atlas entered the solar system, researchers expected another anomaly, but not one that would surpass Oumuamua in complexity. Yet Atlas introduced even more contradictions. Its metallic spectrum, its unnatural stability, its patterned fragmentation, and its aerodynamic anti-tail created a puzzle far more layered than anything Oumuamua had presented. After the controversy sparked by Avi Loeb's arguments, the scientific community became more cautious, choosing their words carefully and avoiding premature conclusions. In this atmosphere of restraint, Atlas emerged as the next benchmark, the new stress test for how we study interstellar visitors. And if Oumuamua was chapter 1 of this story, Atlas feels unmistakably like chapter 2. Borisov, the second confirmed interstellar comet, behaved exactly as science expected. It carried water, produced a bright coma, released gas in predictable ways, and followed patterns consistent with natural objects formed in cold, distant systems. It became the reference point. The model that proved interstellar comets could be ordinary. Then came 3I Atlas, a visitor that rejected every expectation. No water-driven coma, no predictable gas jets, a metallic signature instead of an icy one, a rigid dust structure instead of a fragile tail. The contrast between the two was so stark that Borisov effectively became the control sample, the baseline for what interstellar comets should look like. By that comparison, Atlas stood out dramatically. 2 visitors from the same vast galaxy. Yet only one refuses to resemble anything we thought we understood. The orbit of 3I Atlas revealed one of the most decisive clues about its origin long before scientists understood its chemistry or its strange behavior. As astronomers traced its path through the solar system, they found that its trajectory formed a pure hyperbola, a curve that does not loop back, does not close on itself, and does not bend into a stable orbit around the Sun. It was a clean escape line, a mathematical signature of something that is simply passing through. The Sun's gravity tried to claim it, but Atlas never slowed enough to be captured. It rushed toward the inner system at a speed that exceeded the threshold of gravitational binding and then angled back outward, continuing on a journey that began long before humans existed and will continue long after our species is gone. What fascinated astronomers even more was the cleanliness of its entry and exit angles. As it approached the inner planets, its trajectory showed none of the subtle distortions caused by close gravitational interactions with massive worlds like Jupiter or Saturn. Space is a messy place where orbits are tugged, nudged and sculpted by the weight of giants. Yet Atlas passed as if nothing in the solar system truly touched it. It carved a path so smooth that some researchers described it as a needle sliding through fabric without ever catching a thread. This raised a new question. How could an interstellar object navigate so cleanly through a system full of gravitational traps? The mystery deepened when astronomers attempted to track Atlas backward through space. When they projected its path into the past, they expected it to point toward a star or a stellar nursery. Instead, the trail led into emptiness. A region with no bright stars, no energetic systems, no obvious birthplace. The silence of that origin became its own kind of signal. It suggested that Atlas may have traveled for millions, possibly billions of years in the dark interstellar medium, untouched and unclaimed by any gravitational source. If Atlas originated near a star, that star is no longer identifiable. If it came from a planetary system, that system may no longer exist. Some researchers propose that Atlas could be a relic expelled during the early chaotic formation of a distant system. Others suggested it might be debris from an ancient catastrophe, such as a planetary collision or the collapse of a stellar companion. But none of these theories fully explain why its orbit is so pristine. The lack of gravitational scarring hints that Atlas has not passed near anything massive for a very long time. It has drifted through regions of space where stars are sparse and forces are weak, preserving its path like an untouched fossil imprinted on the geometry of the cosmos. This isolation gives Atlas a strange kind of presence. It behaves like something shaped by emptiness rather than by matter. Something guided not by encounters, but by absence. And if we consider the possibility of structure or intention behind its path, even slightly, the clean hyperbolic orbit takes on an entirely different meaning. It begins to look less like a random arrival and more like a deliberate trajectory. A journey plotted across interstellar space without deviation. Whether natural or engineered, such precision invites a deeper reflection on what kind of object can maintain such a course across unimaginable distances. A natural body should show the memory of past encounters. A constructed one might hide them. The further Atlas traveled through the solar system, the clearer the message seemed to become. It came from darkness, untouched, unaltered and unclaimed, and it will leave in the same state. And as its fading trail cuts away from the sun, a single thought lingers like an echo across the void. It came from the dark, and it will return to the dark. As astronomers directed more instruments toward 3I Atlas, the mystery shifted from its path to its light. Every celestial body carries a reflectance curve, a subtle fingerprint describing how its surface interacts with sunlight. For comets, this curve is soft and irregular because they are made of porous ice and dust that scatter light unevenly. But Atlas defied that expectation. Its reflectance curve rose with a crispness closer to metal or engineered carbon composites. Materials that absorb and reflect light with far greater precision than anything found in natural comet nuclei. This was the first sign that its exterior was flatter and more uniform than it should be. As if erosion, fragmentation and billions of years of radiation had not managed to roughen its surface. That smoothness puzzled researchers because even the most stable comets develop pits, cracks, and irregularities from their long exposure to cosmic forces. Atlas appeared to resist these processes, or perhaps it was built from something that responds differently to time. Another anomaly emerged when astronomers noticed that Atlas's brightness barely changed as it moved closer to the sun. Natural comets brighten dramatically when warmed because sublimating water vapor creates a glowing halo, feeding the coma and tail. But Atlas behaved like a surface whose reflectivity was independent of temperature, rising only slightly and never producing the outbursts expected from melting ice. Observers searched for spectral signatures of water, hoping to confirm at least one familiar behavior, but the spectrum remained stubbornly dry. There was no sign of scattered ice grains, no translucent spikes, no shimmering signatures of vaporized water molecules. Instead, the readings pointed toward a surface that was dense, solid and strangely consistent. This lack of water reflection became even more unsettling when paired with Atlas's earlier chemical anomalies. If the interior contained frozen material, it was being shielded by something that refused to let sunlight disturb it. Some scientists proposed that Atlas might be coated with a crust of sintered dust hardened over eons. Others speculated about carbon structures compressed under extreme heat in some ancient stellar environment. but none of these hypotheses explained the smoothness, the durability, or the peculiar way its light seemed to obey rules more akin to refined materials than natural debris. This led to a more provocative idea, whispered in small corners of academic circles. Perhaps Atlas was not eroded by time, but preserved by design. A surface that does not scatter water signatures, that holds its brightness steady, and that reflects, like metal suggests, intentionality. Or at least a structure formed in conditions radically different from the chaos of comet birth. If Atlas was forged by nature, then it came from a place nature has not shown us yet. And if it was not, then we are looking at something that carries a surface meant to endure a journey through darkness without revealing its age or its purpose. With every new measurement, the identity of Atlas grew more contradictory. It traveled like a wanderer, but reflected light like an artifact. It behaved like an ancient relic, yet displayed the cleanliness of something unweathered. And at the center of these contradictions lies a single truth difficult to ignore. Atlas does not look like any comet we have ever seen. It does not even pretend to. As the scientific community struggled to explain the strange light behavior of 3I Atlas, attention shifted to a deeper and far more unsettling possibility buried beneath its reflective surface. If its exterior does not behave like a natural comet's shell, then what lies inside it? Several structural models began to circulate, each attempting to reconcile Atlas's stability, chemical oddities, and resistance to heat. The most provocative among them suggested that the object might contain a dense metallic core. This idea gained traction not from speculation, but from the undeniable nickel signature that dominated its spectrum. Natural comets do not concentrate nickel this way. The overwhelming presence of this element forced researchers to confront a possibility rarely considered in planetary science. Could Atlas be a composite object, built from multiple materials and forged under conditions so extreme that they mirror industrial refinement more than cosmic randomness? A metallic core would explain many of its behaviors. It would allow Atlas to maintain structural integrity as it approached the Sun, resisting the explosive outgassing that tears typical comets apart. It would also explain why no jets of vapor destabilized its rotation. A body with such an interior would not leak heat or gas easily. It would protect whatever volatile materials lie within and present a hard silhouette to the vacuum around it. More importantly, a core with significant mass at the center would naturally stabilize the object's spin. Many spacecraft use heavy internal components to maintain orientation during travel. The more scientists examined Atlas's nearly perfect rotational rhythm, the more they realized how difficult it would be for a natural object to preserve such balance while drifting through space for millions of years. And the nickel-only composition deepened this suspicion. Nickel is not unusual by itself, but the absence of iron alongside it is. In nature, these two metals form together in countless cosmic environments. Finding one without the other is like finding a fossil with missing bones. It suggests separation, sorting, or purification. None of these processes occur easily in nature, but they appear routinely in engineered contexts, where materials are purposefully isolated and refined. A few researchers wondered whether Atlas might have originated in a catastrophic event so massive it separated metals by density before freezing them into a single structure. Others whispered cautiously that nickel dominance is more reminiscent of industrial metallurgy than cosmic geology. If Atlas is truly a composite object, then its hard surface is not an evolutionary accident. It is a feature. It explains how the object resists erosion, why it released almost no water vapor, and why fragments appeared to break along symmetrical lines instead of chaotic ones. Comets crumble. Atlas fractured with discipline. This difference led to a deeper hypothesis. What if the core of Atlas is designed not only to survive, but to preserve the internal arrangement of the object, even after partial fragmentation? That would imply a level of structural intention that does not align with natural formation, whether built by extreme cosmic conditions or by something capable of shaping matter deliberately. The result is the same. Atlas carries a form that is too orderly to ignore. As astronomers pieced together these clues, an unspoken question began to form in the background of scientific discussions. If Atlas is not natural, then what exactly is it? As 3I Atlas drifted closer to the Sun, astronomers expected a familiar transformation. All comets, without exception, respond to solar heat with a surge of activity. Their surfaces warm rapidly. Frozen compounds begin to sublimate and jets of gas erupt violently into space, reshaping the comet's appearance as it approaches perihelion. But Atlas broke this rule with a calmness that bordered on defiance. Even as sunlight intensified, its thermal signature barely changed. Instruments monitoring its temperature found no significant rise and no sudden bursts of heat that would indicate melting or volatile release. Instead, the object maintained a strangely muted thermal profile, as if the sun's energy were sliding across its surface rather than sinking into it. The absence of jets made the puzzle even more striking. Water-rich comets develop geysers that act like tiny rocket engines, blasting dust and vapor into space. These jets leave unmistakable thermal fingerprints and disrupt the comet's rotation. Yet Atlas displayed neither the jets nor the thermal scars that accompany them. Its stability held firm. Its spin undisturbed, and its surface refused to reveal the chaos normally unleashed by solar heating. This led researchers to examine the heat conductivity of the object. Natural comets are poor conductors, but they still warm noticeably as sunlight penetrates their dusty layer. For Atlas to resist heating so effectively, it would either need to be made of material with extremely low thermal conductivity or be insulated by a protective shell that prevents energy absorption. A solid outer crust could explain the muted temperature line, but the consistency required for such insulation is rare in nature, especially for an object wandering through space for millions of years. The idea of a hard external layer began to take hold. It would shield any internal ice from rapid warming and prevent the release of vapor. It would also explain Atlas's lack of thermal variation and its refusal to develop the bright coma that typically announces a comet's arrival in the inner solar system. Another anomaly made the mystery even deeper. Infrared scans revealed that Atlas emitted far less thermal radiation than expected. Objects exposed to sunlight re-radiate heat, glowing faintly in infrared wavelengths. But Atlas glowed dimly, almost reluctantly, as if whatever absorbed the energy did not wish to release it back into space. This dampened radiation matched the hypothesis of an insulating layer, something dense enough or engineered enough to trap heat within. The possibility unsettled many researchers because it contradicted what comets are supposed to be. Comets are fragile, porous, reactive. Atlas remained silent, dense and unmoved. A few scientists proposed that this insulating layer might be the result of sintering, where dust particles fuse into a hardened crust through repeated exposure to cosmic rays. But even sintered crusts crack, peel, and respond visibly to heat. Atlas did none of these. Its behavior suggested a level of thermal resilience far beyond naturally evolved bodies. And when combined with its metallic spectrum, symmetrical fragmentation, and precise rotation, the temperature anomaly became more than a curiosity. It became part of a pattern. Every new measurement seemed to whisper the same unspoken idea. Something is shielding this object from the sun. Whether that shield is geological, chemical, or engineered remains an open question. But the effect is unmistakable. As Atlas swept past the sun without flaring, melting or revealing weakness, one thought pressed quietly against the edge of scientific certainty. What kind of object wears armor against a star? As 3I Atlas approached the inner solar system, astronomers waited for the same predictable transformation they had witnessed countless times before. Comets brighten as they draw closer to the sun. It is one of the most reliable photometric rules in observational astronomy. Heat vaporizes ice. Gas escapes in luminous streams, and dust becomes illuminated by sunlight. The result is a rapid increase in brightness that can turn even small comets into visible spectacles. But Atlas once again rejected this rule with unsettling simplicity. Instead of brightening, it dimmed. Day after day, telescopes recorded a slow and deliberate decline in its reflectivity. The more sunlight it received, the darker it became. The phenomenon was so counterintuitive that some observers initially suspected instrumental errors, yet every independent measurement confirmed the same trend. Atlas was losing light. It behaved almost like a surface designed to swallow illumination rather than scatter it. This dimming violated the fundamental photometric expectations that govern comet behavior. In standard comet models, brightness increases as the surface releases volatile materials, which then form a reflective haze around the nucleus. A comet that grows darker near the sun defies the very mechanism that defines what comets are. This forced astronomers to consider explanations outside the familiar framework. One possibility was that a thin, dusty coating had been burned away or altered as Atlas approached the sun. Perhaps a dark crust was exposed beneath it, absorbing more light than the original surface. But this hypothesis raised a contradiction. If the crust were natural, why had it not been weathered or eroded over millions of years of cosmic travel? Another idea proposed that Atlas was consuming or redirecting solar energy in a way not seen in natural bodies. Instead of heating significantly or venting jets, it seemed to manage energy quietly, without producing visible activity. This hinted at an energy budget unlike anything expected from frozen debris. A natural comet's brightness rise is tied to energy loss. Atlas dimming suggested energy retention or conversion. Some researchers speculated that the surface might contain materials that undergo phase shifts when exposed to heat, becoming less reflective. Others wondered whether the object could selectively absorb wavelengths of sunlight, behaving more like engineered composites than random dust and ice. What deepened the mystery further was that Atlas did not dim chaotically. The decline in brightness followed a smooth, consistent curve as if governed by an internal threshold or process responding predictably to solar proximity. Natural comets show erratic spikes caused by outbursts or structural collapse. Atlas showed none of this noise. It faded with discipline. Another anomaly emerged during infrared observations. As Atlas dimmed in visible light, it did not emit the corresponding increase in thermal radiation expected from a surface absorbing more solar energy. In simpler terms, Atlas got darker without getting hotter. This discrepancy widened the gap between what scientists expected and what Atlas delivered. A surface that darkens but does not heat up behaves unlike rock. Ice or dust. It behaves like a material intentionally resisting photometric analysis. It became increasingly difficult to ignore the pattern emerging across all measurements. Atlas brightened less than a comet, heated less than a comet, and dimmed more than a comet. It was performing an optical vanishing act as though trying to reduce its visibility at the exact moment when observers should have seen it most clearly. Some scientists described this behavior as a defensive response, while others viewed it as a passive consequence of unknown chemistry. But the question persisted with growing gravity. Why would an interstellar object begin to extinguish its own light as it approached a star? And what truth lies hidden behind that fading luminosity? As 3I Atlas carved its way into the inner solar system, astronomers began to notice something profoundly unusual about the geometry of its path. Most comets arrive through predictable corridors shaped by the gravitational architecture of the outer planets. They are guided, nudged, and often perturbed by the invisible hands of Jupiter, Saturn, or the Kuiper Belt before they make their inward plunge. But Atlas entered from a direction almost untouched by these familiar influences. Its trajectory approached the Sun from a region rarely used by inbound objects. A corridor so empty and dynamically quiet that few celestial bodies ever passed through it. This alone was enough to draw attention. But the mystery deepened when researchers measured the angle of its descent. The approach was too clean. Natural comets often drift toward gravitational wells and pass near massive bodies that bend their routes. They are constantly being kissed by stars, planets, and the tidal forces that shape cosmic motion. Atlas, however, slipped past such interactions with uncanny precision. There was no sign that its journey had been altered, slowed, or distorted by any major gravitational field. The implications of this purity were difficult to ignore. For a natural object wandering through the galaxy, such a path would require improbable luck. It would have had to avoid dense star clusters, bypass rogue planets, and slip between stellar remnants without ever being pulled off course. The universe is full of gravitational traps that distort trajectories. Atlas behaved as though it had avoided them all. Some astronomers proposed that Atlas might simply have traveled through an exceptionally empty region of space. But even in emptiness, cosmic drift and random encounters usually leave subtle imprints. Atlas showed none. Its path into the solar system resembled a line drawn with intent. A trajectory so precise that even a spacecraft would struggle to replicate it without careful navigation. This led to speculation, whispered at first and then spoken with increasing courage, that Atlas might not be responding to gravitational forces the way fragile icy bodies do. It moved more like an object with mass distribution optimized for stability, or like something capable of resisting perturbations through means we do not yet understand. Whether these properties were natural or deliberate remained unknown. But the consequence was clear. Atlas arrived on a path too perfect to dismiss. It approached the sun as though it were following instructions written long before humanity learned to look up at the sky. And as it curved into view with its impossibly clean trajectory, one question began to echo quietly across academic circles. Was this path a product of nature, or was it guided? When astronomers attempted to push Atlas backwards through time, following its hyperbolic path into the depths of the galaxy, they expected at least one familiar signpost. A faint stellar nursery, a dying star, a dense molecular cloud, or any recognizable environment that could have forged an object with such unusual properties. Instead, the projection led them into emptiness. No bright stars, no active clusters, no warm nebulae. Only a silent patch of interstellar space with nothing to mark its past. This unexpected origin became even more confusing when paired with the nickel-only anomaly. A composition dominated by nickel suggests exposure to intense heat, the kind produced in violent stellar environments. But the region indicated by trajectory backtracking holds no such engines of creation. It is cold, quiet, and painfully uneventful. Two truths stood side by side and refused to reconcile. The orbit said Atlas came from darkness. The chemistry said Atlas came from fire. How could both be true? Some researchers proposed that Atlas was born near a star that no longer exists. Perhaps a supernova erupted ages ago, scattering its remnants across the void and sending Atlas spinning into interstellar exile. Under this scenario, the nickel signature might be the scar of that ancient explosion. But there was a problem. Supernovae leave behind traces, shock fronts, radiation shells, metal-rich debris fields. None of these can be found along Atlas's projected path. Others theorize that Atlas might once have orbited a star that has since migrated, leaving its former debris trailing behind in the cosmic dark. But stars do not vanish without leaving heat signatures or structural imprints in the surrounding region. The further researchers pushed the simulations, the stranger the mystery grew. It was as if Atlas had slipped into the galaxy from a place that does not appear on any astrophysical map. A possibility even more unsettling emerged when considering the object's fragmentation behavior and stable rotation. These traits suggested internal structure and resilience, features rarely produced by chaotic natural formation. Some scientists began to ask whether Atlas might be older than the stars nearby. Perhaps a relic from an early epoch of the galaxy when conditions and processes differed radically from the ones we know today. Under this view, Atlas could be a survivor from a long vanished environment. A fossil from a chapter of cosmic history erased by time. But even this hypothesis does not fully explain its chemical purity or its immaculate trajectory. That led to one final, whispered theory, spoken cautiously because of its implications. Perhaps Atlas did not come from a place that still exists. Perhaps its birthplace was destroyed, consumed, collapsed, or transformed into something unrecognizable. A ruined star, a burned out system, a forgotten collision of giants. If that is true, then Atlas is not just a visitor. It is a message in motion, the last surviving witness of a world the universe has already erased. and as it drifts silently across the void, one question lingers like an echo that refuses to fade. What kind of place must it have left behind? While official agencies struggle to keep pace with the unfolding mystery of 3I Atlas, a parallel stream of data quietly emerged from a different community. Amateur astronomers scattered across Europe, South America and parts of Asia had been monitoring Atlas long before NASA released its formal updates. Their equipment might not match the power of professional observatories, but their advantage was immediacy. They observed constantly, without bureaucratic delays or data embargoes. And what they documented painted a picture far stranger than the cautious reports issued by major institutions. The first inconsistency appeared when amateurs publicly noted the fragmentation of Atlas earlier than NASA acknowledged. Through long exposure imaging and stacked photometry, observers in Spain and Brazil identified faint subcomponents peeling away from the main body weeks before any official bulletin mentioned structural instability. These early reports circulated through niche forums, gaining traction as more observers replicated the findings. The fragments appeared evenly spaced, almost symmetrical, contradicting the chaotic patterns expected from natural shear or thermal cracking. Yet NASA's updates remained minimal, referencing fragmentation only after the amateur community had already mapped several pieces. A second wave of irregularities came from enhanced imaging shared online. While NASA published blurred or low detail frames, amateur astrophotographers posted surprisingly sharp images showing textural gradients across the core, suggesting variations in surface hardness or reflectivity. Some images even showed an odd shimmering effect, a rapid oscillation in brightness that did not match atmospheric distortion. The phenomenon was later confirmed in videos captured from Chile and Italy, where Atlas flickered with a periodic variation too fast and too stable to be random. These light fluctuations raised troubling questions. Was Atlas rotating unevenly? Was something inside shifting? Or was the surface itself reacting to sunlight in a way unknown to natural comets? NASA did not address these anomalies. It did not deny them either. This silence allowed speculation to grow, widening the informational gap between independent observers and official channels. The amateur community continued documenting each shift, each pulse, each fragment, and slowly a realization took hold. The clearest view of Atlas did not come from government agencies. It came from scattered telescopes in backyards, rooftops, and countryside hills. Together they revealed a version of Atlas too strange to fit neatly into official narratives. And as those images spread, one unsettling truth became harder to ignore. The gap between what is observed and what is reported is no longer small. It is widening. As Atlas approached its closest point to the inner planets, a new thread of curiosity emerged from an unexpected source. Amateur radio astronomers, scattered across multiple continents, began noting brief spikes in their readings. These were not messages, not structured signals, and not anything resembling intentional communication. They were simply short bursts of radio intensity, lasting only seconds, occurring at roughly the same time frame that Atlas moved into high illumination. The first report came from an operator in Finland. who detected a sudden narrowband spike near the VHF range. It lasted less than 2 seconds. Within hours, a hobbyist in southern Brazil reported a similar anomaly. Then another in Germany, and later one in New Zealand. None of these observers knew one another, yet their logs revealed patterns too closely aligned to ignore. The spikes were brief, isolated, and seemed to occur only while Atlas crossed certain angles relative to the Sun and Earth. Efforts to attribute the bursts to solar flares quickly fell apart. Solar activity at the time was quiet, and space weather archives confirmed there were no geomagnetic disturbances that could mimic the readings. The signals, faint as they were, did not resemble atmospheric reflections or satellite interference. They appeared to come from directionally fixed space, yet they also lacked any modulation that would classify them as artificial transmissions. They were simply anomalies, too regular to dismiss, yet too incomplete to interpret. When asked, SETI researchers declined to comment. Silence can mean many things. Perhaps the signals were too weak to matter. Perhaps the data was inconclusive. Or perhaps comment was withheld to avoid speculation. Still, the coincidence hung in the air. Why would radio receivers across multiple continents detect a brief spike precisely as an interstellar object passed through a specific geometric window? Was it a reflection of solar activity on an unusual surface? Was it interaction with the object's metallic signature? Or was it something produced internally and unintentionally by the structure of Atlas itself? Whatever the source, the spikes vanished as quickly as they appeared. No repeating pattern, no extended emission, just a fleeting whisper lost in the ocean of cosmic noise. Yet even a whisper can change a conversation. And for many, following the trajectory of Atlas, that momentary flicker of radio energy became a question with no comfortable answer. As 3I Atlas moves along its outbound curve, a rare alignment draws near. On December 19, 2025, the object will pass at a distance that allows unprecedented clarity for observation. Interstellar visitors seldom come this close to Earth. Oumuamua passed quickly and faintly. Borisov was fast but familiar. Atlas, however, brings with it a trail of contradictions and unanswered questions that make this approach one of the most anticipated events in modern astronomy. Telescopes around the world are preparing for the moment, but none hold more potential than the James Webb Space Telescope. With its infrared sensitivity and spectroscopic precision, JWST may be able to extract the chemical fingerprints hiding beneath Atlas's enigmatic surface. It could confirm whether the nickel dominance is real. It could detect silicates, carbon structures, or even exotic compounds unseen in natural comets. The data could validate decades of cometary models, or break them entirely. Ground-based observatories are also gearing up for the encounter. Large arrays in Hawaii. Chile and Spain hope to capture high-resolution images of the dust environment around Atlas. If the object truly lacks the typical water-driven coma, these images will reveal the structure of whatever faint material remains. For the first time, scientists may see the boundary between fragments, the nature of the outer shell, and any possible vents or fissures. Amateur astronomers too are preparing for their moment. Their earlier observations proved invaluable, and many expect this pass to offer the clearest look yet at Atlas's rotation, brightness changes, and fragmentation pattern. Every continent will contribute frames to a global mosaic that may become the definitive portrait of the object. But beyond the excitement lies something more profound. This is one of the only opportunities humanity will have to look directly at a visitor from beyond our planetary family. Not through blurry distant frames. Not through brief encounters hidden in noise. But through coordinated eyes across the entire planet. And if Atlas carries secrets that have eluded us until now, this moment may finally force them into the light. Whether the object reveals its nature or guards it more fiercely remains to be seen. But on that December night, as telescopes turn toward a point of moving starlight cutting across the dark, one promise hangs in the air. If Atlas has truths to reveal, this is the moment they will emerge. As 3i Atlas continued to defy the expectations of astronomers, the scientific community found itself split across a widening field of interpretations. Each new observation challenged conventional understanding, and every anomaly forced researchers to choose a side. The debate became a tapestry of competing theories, each one attempting to reconcile the impossible. The first and most conservative theory insisted that Atlas was entirely natural. According to its proponents, everything unusual could eventually be explained by rare physical conditions or incomplete data. To them, Atlas was simply a comet shaped by an extreme environment we had not yet modeled correctly. But this explanation weakened with every contradictory measurement. The second theory proposed that Atlas was a relic of a dead star system. Perhaps the surviving fragment of a catastrophic celestial event long forgotten by the galaxy. Its nickel-rich composition, hard shell and thermal resilience hinted at an origin forged in intense heat before being flung into interstellar space. This scenario fit some data, but it struggled to explain the precision of Atlas's spin and trajectory. A third theory suggested that Atlas might be a shard of a metal-rich planet, torn apart by gravitational collapse or collision. Such a fragment could possess a metallic core and solid exterior. But this view faltered when confronted with Atlas's fragmentation symmetry and persistent energy stability. And then came the fourth theory, whispered first in private discussions and gradually spoken aloud. The idea that Atlas might be a remnant of ancient technology, not a functioning machine, but a fossil of engineering older than any civilization we know. Its nickel purity, hard insulating shell and controlled spin all resemble design principles rather than geologic happenstance. Most scientists rejected this hypothesis publicly, but the data did not entirely cooperate with their skepticism. With each new contradiction, the question grew sharper. Which theory aligns best with the evidence? And which ones are we clinging to simply because the alternative feels too large? Among the most unconventional theories to emerge, one stood out, not because it was likely, but because it fit the anomalies more neatly than expected. A small group of fringe researchers began comparing Atlas to a biological cell, not a living organism in the earthly sense, but a cosmic scale container engineered to preserve internal material across impossible distances. They pointed to Atlas's shape, its length to width proportions, and its surprising thermal retention. These traits resembled principles found in extremophiles and microbial cell walls, where the ability to maintain internal temperature despite external radiation is crucial for survival. The near total absence of water loss fascinated these theorists. Natural comets bleed moisture rapidly. Atlas held it. The The fragmentation pattern added fuel to their speculation. Instead of chaotic breakup, Atlas appeared to divide along structural seams, almost like programmed partitioning. To these researchers, the 16 fragments resembled the earliest stages of cell division, scaled up by astronomical magnitudes. They argued that in a universe governed by chemistry, life may not only emerge, but also move. It may build vehicles for its own migration. If that is true, they wondered aloud, could Atlas represent a form of cosmic transport? A shell carrying biochemical potential across the galaxy? A vault for seeds of life? Or something even more abstract, like a carrier of encoded chemical information meant to survive epochs longer than stars themselves? Most scientists dismiss this speculation as poetic rather than practical. But the odd consistency of Atlas's behavior left the door slightly open. And as they examined the uncanny parallels between biology and structure, one question lingered in the shadows. What if life does not only arise? What if it travels? As the anomalies accumulated, a more radical interpretation took shape. A minority of researchers began to propose that Atlas might not be a natural object at all, but rather a dormant interstellar probe, or the remains of one. They pointed first to the nickel-only composition, which mirrors the purity found in industrial smelting rather than natural mineral formation. In nature, nickel and iron appear together almost inseparably. Their separation suggests refinement. Then there was Atlas's remarkably stable spin. Natural comets tumble, wobble and drift unpredictably. Atlas rotated with the steadiness of a machine, almost like an object designed to maintain orientation. Even the hard outer shell aligned with engineering logic. A protective layer capable of resisting extreme thermal environments would be essential for any probe traveling between stars. Such a shell could also shield internal components or volatile materials, explaining Atlas's muted thermal profile. The fragmentation pattern further emboldened the hypothesis. Instead of disordered breakage, Atlas fractured into 16 well-spaced pieces, each maintaining relative stability. To an engineering mind, this looked less like failure and more like deployment. The controlled separation of modules. If that were true, then Atlas was not breaking. It was operating. But operating toward what end? And who could have built it? The scale of the question made many uncomfortable. Humanity has not yet launched anything capable of surviving interstellar travel. The idea that another civilization, ancient or extant, might have done so challenges the boundaries of scientific caution. And yet, the data align too neatly to ignore. Nickel purity, stability, heat resistance, symmetrical fragmentation, a trajectory that behaved like navigation rather than drift. None of this proved the probe hypothesis, but every anomaly nudged the idea further from fiction and closer to possibility. And in the quiet tension of academic debate, one question began to surface with a weight that made even skeptics pause. If Atlas is a probe, then who sent it? When news of 3I Atlas spread beyond scientific circles, public imagination quickly turned toward one question. Could it hit Earth? The fear was understandable. An interstellar object behaving strangely. Fragmenting and darkening near the sun sounded like the setup to a cinematic disaster. But mathematically, the answer was clear. Atlas would not collide with Earth. Its hyperbolic trajectory ensured a clean departure. Yet, this did not mean its passage would be without consequences. Even without a direct hit, an object of Atlas's composition and behavior can influence our cosmic environment in subtler ways. Some researchers explored whether its proximity could interact with Earth's magnetosphere, not through impact, but through the charged dust or unusual reflective properties altering how solar radiation propagates in the surrounding space. Others examined the optical complications it might introduce. A dimming object with shifting reflectance could confuse early warning systems designed to track near-Earth objects, creating false positives or masking genuine threats. The fragmentation of Atlas introduced another layer of complexity. 16 fragments moving through space create a dust stream, a trail of fine particles that could intersect Earth's orbit months or even years later. Such streams have historically produced meteor showers, ionospheric disturbances, or minor atmospheric heating. None of these outcomes pose existential danger, but they leave fingerprints small yet measurable. And even if Atlas poses no threat of collision, it leaves behind a different kind of impact. It forces humanity to confront how little we understand about interstellar visitors. It exposes limitations in our models and gaps in our detection capabilities. And it challenges our confidence in predicting the behavior of objects that do not follow the rules. Atlas will pass harmlessly by, continuing its silent journey, but traces of its presence dust. Data and questions will linger long after it fades into darkness. And as we watch it recede across the sky, one thought remains impossible to ignore. Even without touching Earth, Atlas will change the way we see the universe. As 3I Atlas completes its brief passage through our solar system, its trajectory bends outward, accelerating gently under the diminishing pull of the sun. In a matter of months, it will fade beyond the reach of even our most sensitive telescopes. There will be no return, no second chance, no future rendezvous. Interstellar objects come once, reveal a fraction of themselves, then disappear into the endless dark. Every measurement taken now is irreplaceable. Every observation, a moment that will never repeat in the entire history of humanity. And while Atlas itself will vanish, its fragments follow slightly diverging paths, thin threads of destiny spinning away into the void. Some may drift silently for millions of years. Others may collide with dust clouds or pass near distant stars. They are the only physical traces of a visitor we barely understood. One day, long after we are gone, another civilization may detect them and ask the same questions we ask now. But for us, this encounter is final. Atlas came, we watched, and now it returns to the darkness from which it emerged. A visitor we will never see again. As the world prepares for Atlas to fade from view, a quieter realization settles into the scientific community. There are still gaps, still unanswered anomalies, still files we have not seen. NASA has yet to release a complete dataset from the Mars flyby, including high-resolution frames that could confirm or dismiss several early claims. The nickel-only signature has gone unexplained, left hanging in reports with no further comment. The unnaturally stable spin has been mentioned but not addressed. and the anti-tail. One of the most visually striking anomalies is almost entirely absent from official summaries. These omissions do not imply conspiracy. They imply limitation. Perhaps the data is inconclusive. Perhaps scientists do not yet agree on interpretation. Or perhaps the truth is simply stranger than any of the safe explanations we prefer. The universe does not hide from us. It reveals itself constantly. But revelation means nothing if we do not look in the right direction. And Atlas, in its silence, forces us to reconsider where we have been looking all along. In the end, 3. Atlas is more than a scientific curiosity. It is a mirror, a reminder of how small we are compared to the scale of the cosmos, and how much of existence remains hidden beyond our reach. The arrival of an interstellar visitor is not a rarity, but a revelation. These objects have likely passed through our solar system long before we had eyes to see them or instruments to measure them. Atlas simply happened to arrive at a moment when we were finally capable of noticing. Yet, even with modern tools, we observe only a sliver of reality. Humanity has explored perhaps 1/10,000% of the observable universe. Everything we know is a fraction of a fraction, and so Atlas becomes more than a mystery. It becomes a message. A reminder that the cosmos is deeper, stranger, and more crowded than we imagine. If Atlas is the third interstellar object we have identified, how many have we missed? How many passed silently through the solar system centuries ago? And how many more are already on their way? And so we arrive at the final moment of our journey with 3I Atlas. A journey built not from certainty but from questions. We have followed a visitor from beyond the stars, examined its nickel-rich skin, its silent spin, its impossible fragmentation, and the silence that surrounded it. But understanding does not come from forcing an answer. It comes from holding the question long enough for truth to reveal itself. Science was never meant to be a collection of conclusions. It is a discipline of curiosity, a commitment to doubt, a refusal to stop looking. Atlas challenges us not to believe, but to investigate. Not to accept, but to examine. And as it fades into the dark, we are left with a choice: to let the mystery close, or to let it open us. If you wish to continue exploring the universe with us, you are welcome to stay, to listen, to question, and above all, to remain awake in a cosmos full of wonders. Stay curious, stay critical,